It actually a temperature dependent term. Okay, therefore we can use this Arrhenius equation to describe the temperature dependent of K. Okay, when you see Arrhenius equation, bear in mind that basically we have to use this equation to determine the reaction rate constant K. Okay, and this Arrhenius equation is K equal to A times E, the power of minus E over RT. Okay, and this one, right, as you know, K is actually the rate constant, reaction rate constant. And in order to carry out the reaction, right, remember that molecule, for example, A plus B, in order to give C, okay, A plus B, it must have enough collision, okay, in order to have A attack to B, right, to give you the product C. Okay, another important factor is, even though when A actually collide with B, right, it also will be depends on the frequency factor. Okay, this frequency factor is considered as the Arrhenius constant. On top of that, in order to get the product C, right, one mainly important thing is what is the activation energy, okay? And activation energy will be constant, right? Regardless any temperature, the activation energy is still the same. For example, for this A and B, A and B is considered as reactant, right? This is the energy level. A and B, when it's collide together, it will go to the intermediate, right? After that, you will get product C. Okay, and in this particular intermediate, the one that has the highest energy level, okay, compared to this one is the energy level of your reactant, right? At first, A plus B, this is the energy level of the reactant, and this is the product C, is actually energy level of your product. Okay, in order for A to give you the product C, right, A and B must make sure that it actually has higher energy, more than the activation energy, or EA. This activation energy, the energy that actually implement to A and B, must be higher than EA. Okay, in order to have this reaction go forward. Okay, that's why activation energy, I can say that basically is the key lah. Okay. And of course, the main factor in order to push the reaction move forward, it will be mainly through the temperature. Okay, temperature will play a very big important part. Okay. Another important factor is the R. R is the universal gas constant. These are the unit. The number is 8.314 joule per mole per Kelvin. This is constant, so it fixed across all the temperature. Okay, and this frequency factor, it means that molecule A and B are attacked together, right? And this one will be mainly also depends on the temperature. Okay, of activation energy is the minimum energy that molecule require to collide before it gives to the product CR. Okay, and based on this Arrhenius equation, the increasing of temperature, it will be increased to the rate of equation, the reaction rate constant. Okay, let's look at a common term of rule state that the rate of reaction will be double every 10 degrees increase in temperature. Okay, this one will be estimated. Okay, regardless, it also have to depend on the experiment that you obtain from your actual experiment. Okay, how can we actually get the information? This is the Arrhenius equation. How can we use this equation in order to find out what is the K? Okay, so basically the main concept of this is we have to use this we have to convert this Arrhenius equation to something that you can use the information to plot your graph. Okay, and the graph will be on your lecture note page 19. This will be your lecture note page 19. Okay, how can we convert this into the something that can convert you to the graph? Okay, because this reaction rate constant is equal to A times e to the power of negative e over RT. Okay, so this e is actually the natural exponent number, right? And from this formula you can see that in the case that the temperature is higher, K will be higher, will be increased also because of this exponential. Okay, based on this formula, we can actually take into consideration to put ln both sides. So for the first one will be ln K, okay, and ln all this thing together. Okay, after that we rearrange. The ln K here is the same thing. Ln A we take out because ln A can be ln A plus ln E to the power of minus E over RT. Okay, and because of the log rule of this one you can bring it down. Ln E over E will be, this one the whole thing you can bring it down. Because this one you can cut, right? And then you can put this one back to the front. And after we work it out, ln K equal to ln A minus E over RT. Okay, now because in order to use this piece of information to plot the graph, so what do we need here? Of course, we need what is y, right? X left, how? And also the graph. Okay. From the graph itself, we have to make sure that the formula that we have here, it must be something very similar to the y equal to mx plus c. Okay. Y is here, x is here. M is actually slope, right? Yes, okay. The slope, how can we get the slope? It also depends on the data that we collected, okay? We actually have a very good examples for you to have a look later. Okay, so for now, we come back to this equation a little bit. This equation, we rearrange, we rearrange. So when we rearrange, we got ln k equal to minus e over r times 1 over t plus 1a. Okay, so what is this? This, if you link to the y equal mx plus c. Okay, so you can see that y is ln k, right? Can you compare this? Y is ln k. M is minus e over r. Y is ln k. M is minus e over r. X left. X is 1 over t. C is actually ln a. Okay, basically this idea is, in order to have this, right, this is the information that you should be able to link up. Okay, so now we can use the information here. We plot the graph between the information here, and you will basically get the straight line. And do take note that the slope is actually minus, right? It means that the slope will be decline. Okay, you can refer to your lecture note page 19 now. Okay, lecture note page 19. I write out again one more time. Ln k equal e over r 1 over t plus ln a. Okay, and you can see that compared to y equal mx plus c. C, right? C is the intersection here. Consider as ln A. Okay, because when you start plotting the graph, this is the point that A, it actually hit to the y-axis all the way, and this is the slope. The slope is actually decline, right? All the way until here. Okay, how can we use this Arrhenius equation to find out the rate constant? Okay, the idea of this, the Arrhenius equation, we have to find out rate constant or activation energy. Okay, and how are we going to find out? We have the next example, next very good example for you. Okay, refer to your lecture on page 20. For this example 2.7 now, this will be the last examples already, for your topic 2. And listen to this to me carefully. These examples also I put two star. Okay, I cannot say that which one is will be coming out inside the quiz, but this one 2 star. Okay, I'm not allowed to say which one is coming out. Okay, look at this question. This question is what do we have here is the reaction rate constant K for second order reaction. You see, K for second order reaction is this much at 3 degrees Celsius. And another K at this temperature. Okay, so now you can see that there are two different K now. Okay, and you have to calculate the activation energy of this reaction. Okay, usually what you see is the reaction rate constant will be provided like this. Okay, because reaction rate constant will be different according to the temperature. Okay, because reaction rate constant is actually dependent on the temperature. But the activation energy will not depend on the temperature. Okay? Activation energy depends on the reaction. Therefore, even different in temperature, the activation energy is still remain the same. Okay? Therefore, we can use this piece of information to calculate the activation energy. Okay, how to do this question? According to the Arrhenius equation, was so long. This is Arrhenius equation. Okay, based on the Arrhenius equation at 3 degrees Celsius. Okay, and this 3 degrees Celsius, right? Because do remember that the temperature that we have here, it must be at Kelvin. Okay, so how can we change this 3 degrees Celsius to Kelvin? Plus 273.15. And then you get 276.15 Kelvin. Okay, at this temperature, right, at 276.15 Kelvin, the reaction rate constant of this is 8.9 times 10 to the power of minus 3. Right? This is the information provided from the question. You see, because this question, you can see that the information provided is the reaction rate constant of at the temperature 3 degrees Celsius and 25 degrees Celsius. So you look at the first 3 degrees Celsius, K is this much. Okay, if we refer back to the Arrhenius equation, okay, and when we substitute when we substitute this number into the Arrhenius equation, what we have, it will be this one, right? K, we replace K with this part equal to A, activation energy, frequency factor exponential minus E over RT. R is a consistent. The number is 8.31 Joule per mole per Kelvin. And this is considered as the equation 1. Okay, because this is at the temperature 3 degrees Celsius. Okay, what about at another temperature? Another temperature basically, it actually will give us another equation, right? What is another temperature? At 35 degrees Celsius. 35 degrees Celsius, it actually consider you plus 35 plus 273.15, you get 308.15 Kelvin.
10 to 4.
And the K, it actually from the equation 7.1 times 10 to the power of minus 2. And now we substitute this one back to the main Arrhenius equation. So what we have, we will get equation 2. So now we have equation 1 and 2. Okay, I see that someone still need more time,
Kalau just letak kat YouTube.
Okay, look at this, the equation 1 and 2, right? Let's say now equation 1 we have two unknown, A and E, right? Equation 2 also have A and E. Okay, so now let's say if we combine these two together, we put equation 2 divide over the equation 1. Okay, what we will have, here we put equation 2 over equation 1. Remember to put your unit also. Because the unit is as important as the number. Can I move forward? Or move backward? After this, you still have class, right? From 4 to 6. Wow, so hardworking, everyone. Tomorrow, see me again. Okay, welcome. Tomorrow, I still come to school. If you want to see me, you can look for me. Okay, and now we work it out. I work it out the number because A here, right? The A here, we can cut together, right? A, cross A by A. After that, this number will be, use the calculator, 7.978. And this is another portion. Okay. So now, right, we have to find out this E, activation energy. Okay, this activation, okay, basically, how are we going to remove this exponential E? How? Yeah, we take ln, right? Okay, both sides, and then you will get, oops. Ln 7.978, and this ln the whole thing.
Okay. Oh, tadi yesterday. I mean, yesterday was okay lah.
Okay, in these examples, I actually show you how to do the calculation step by step. Okay, that's why there are a lot of things. But I think if I give you in detail like this, when you go home, you actually can refer to the lecture note, and then you should be able to understand by yourself, okay, by using this lecture note. But because some of you already very familiar with do this kind of calculation, right? So some of you can do very fast one.
So she shifted people around. Yeah, because kan kakak dia baru letak kan. So she changed kakak dia.
Okay, after this, what happened is this ln, right, equal to, use your calculator, 2.077, and the ln E here, we move to the one in front, and this one will be minus. But because it's already have minus, so become plus. Alright, this portion you move out. Because this one will be 1, you move out. This portion, because this is over another value, right? This one will be minus. But minus plus minus become plus. Right? It should be like this. I show you. Okay, it should be like this. Correct? But because this minus and minus become plus. Okay? And after you work it out, activation energy will be 4.585 times 10 to the power of 4 joule per mole.
Dia macam nak kasi air mata dia keluar.
Tapi macam tak.
Okay, done right? Consolidate one more time, huh? Consolidate one more time. You see, I emphasize so many times, huh? So must be something, right? Okay? Look at this question. Okay? Digest slowly one by one again, one more time. This. Okay? When you see this question and then the question asks you to find out the activation energy. When the question asks you to find out the activation energy, in your mind, you should know that, oh, this must be from the Arrhenius equation, because that is the only equation being taught in the lecture, right? Okay? In order to find out the activation energy from this equation, in order to find out activation energy, the E here, you can see that the information provided will be K according to the each temperature. Okay, first K at 3 degrees Celsius, another K is at 35 degrees Celsius. Okay, so after you know that, hey, this temperature is 3, this temperature is 35. Now, in each temperature, you substitute the number of the rate constant into the Arrhenius equation. Okay, this one will be at one temperature will be one equation. Another temperature will be another equation. This one I consolidate. After that, how? Equation 2 divided by the equation 1. Okay? And you will have those activation energy like this. Okay? After that, you put ln, right? And then you can calculate the activation energy already. Can? So if I see anyone did not do it correctly, for the quiz, I agree like that. Okay, so now we finished topic 2 already.